Ladies and gentlemen, welcome to a short project introduction to MefHySto, the Metrology for Advanced Hydrogen Storage Solutions project. I'm Michael.maiwald, I'm the coordinator of the project, and this is co-funded by the European Union's Horizon 2020 Research and Innovation Programme and the MPR participating states. Metrology for Advanced Hydrogen Storage Solutions addresses the need of large-scale energy storage, which is required for a shift to renewable energy supply. Such storage is required for supply of energy at peak times when renewable energy sources fluctuate. The goals cannot be reached without advanced energy storage solutions, like for instance hydrogen storage, and also measurement science is critical for the realization of this commitment. In this project, 14 partners came together, research institutes, universities and companies, to work in 5 different technical work packages on these questions. Renewable energy sources fluctuate significantly, and chemical storage of hydrogen is the most promising solution to avoid disruptive effects in energy supply. Depending on the amount, the availability to convert to energy, and the required purity, 3 different storage types are currently discussed for hydrogen. Medium-sized, safe, reversible storage in solids, either hydrides or adsorption in porous media, insertion in the natural gas grid, or underground storage in geological cavities. However, reliable standards, reference methods, and materials are required for these 3 storage types. Let me briefly introduce the specific objectives of this project, which are located in 5 work packages. In work package 1, the quality of hydrogen produced from proton exchange membranes, water electrolysis, during rapidly imposed transient use periods, that means up to 200% peak load, is assessed with online gas analyzers for measuring key impurities. This includes water vapor and oxygen. The goal of work package 2 is to improve the reference equations of state used for modeling hydrogen injection up to 20% by volume for energy metering, providing traceable density measurements with lowest possible target uncertainty. This serves as the basis for accurate determination of calorific values of energy gases. In work package 3, we investigate sustainability and reliability of fuel cells, whose performance is also affected by impurities in hydrogen and air. Therefore, loss of performance tests are performed on single-cell and short-stack fuel cells. At the end of the project, we aim at giving specifications and recommendations for air quality sensors may be needed for monitoring fuel cell systems. Work package 4 deals with reversible hydrogen storage technologies. We want to provide validated methods for measuring and calculating heat conductivity of hydrogen absorbed and adsorbed in intermetallic material or porous materials as a function of temperature, pressure and other operation parameters. Finally, we want to develop harmonized methods with low uncertainty for stored hydrogen. Last but not least, large-scale storage of gases in geological storage facilities are addressed in work package 5. Here we want to tackle metrological and thermodynamic issues in underground gas storages and the conversion of existing underground storages from natural gas to hydrogen. For more information, please visit our web pages. You'll find more information there, literature, and also more detailed information on the work packages. Also, you'll find further videos on the work packages. Finally, thank you very much for your interest. We hope to see you face to face whenever it is possible. Stay safe. Thank you very much.
Work Package 1 of the MefHySto project looks at new metrology for hydrogen quality from power to hydrogen. The project partners in Work Package 1 include NPL of the UK, PTB and DBI of Germany, CEA of France, and Reganosa of Spain. Online gas analyzers for measuring key impurities in hydrogen, water vapor and oxygen are used to assess the quality of hydrogen produced from PEM water electrolysis. Measurements are required during rapidly imposed transient use periods, requiring fast response times of a few or tens of seconds, similar to the timescale of surges in electricity demand and supply. To meet the need for hydrogen quality analysis, MefHySto will look to develop new metrology for realization and measurement of key impurities in hydrogen with fast response times. PTB will use their expertise in humidity generation and laser spectroscopy to characterize a fast-responding water vapor spectrometer for use in hydrogen. NPL will develop new facilities to make step changes in water vapor and oxygen content of hydrogen. They will use their primary standard for dynamic production of humidified hydrogen to test commercial hygrometer response times in the range of 10 micromoles per mole to 0.5% of water vapor. Reference gas mixtures with oxygen levels ranging from 5 to 15 micromoles per mole in hydrogen will be prepared for use with the new facility developed in MefHySto to test commercial oxygen analyzer response times. With these newly established facilities, NPL will test and validate commercially available instruments with a range of measurement principles that measure the key impurities of water vapor and oxygen in hydrogen. The instruments will be tested for background gas species and pressure-dependent effects on the measurement error. Response times to rising and falling step changes of water vapor and oxygen content will also be assessed. PTB will use their own dynamic humidity standard for the validation of the water vapor spectrometer characterized in their previous work. At NPL and CEA in the laboratory, single-cell PEM test systems will be established with online impurity measurement at the cathode. The output of the electrolyzers will be validated with measurements of water vapor and oxygen contaminants at the exhaust, with the instruments characterized in the previous work at PTB and NPL, as well as a micro-GC. The electrolyzers will operate at different temperatures and current densities to see the effect on contaminants produced, and replication of real-world use with rapid changes in electrolyzer operation will be performed. In the field, the laboratory micro-GC will be connected online to a working PEM electrolyzer test system at Reganosa to analyze contaminants.
Work Package 2 aims at developing thermophysical models for hydrogen-enriched natural gas mixtures, which in turn will characterize hydrogen mixtures under geological storage conditions. The partners collaborating in this work package are the University of Valladolid and Reganosa from Spain, the National Physical Laboratory in the United Kingdom, and the Federal Institute for Material Research and Testing, BAM, and DVGW in Germany. The injection of hydrogen into the natural gas grid offers an energy storage option for renewable sources such as solar and wind. It uses the existing natural gas infrastructure to store and distribute this energy source. Equations on states are needed to estimate the properties of the hydrogen-enriched natural gas mixtures and to provide necessary information to convert the measurements of volumetric flow meters to mass and energy units. BAM will provide to this work package certified reference gas mixtures gravimetrically prepared. The two types of mixtures are multi-component certified reference gas mixtures of standard natural gas with different amounts of hydrogen, up to 20% of hydrogen, and binary certified reference gas mixtures of hydrogen with different natural gas components in varying concentrations. Regarding the multi-component mixtures of standard natural gas with different amounts of hydrogen, the University of Valladolid will analyze the influence of the hydrogen content in the saturation curve of natural gas using a cylindrical microwave resonator. DVI will study the potential content of condensable hydrocarbons following a standard procedure. For the binary gas mixtures of hydrogen with different components of natural gas, the University of Valladolid will measure the density and speed of sound over wide range of temperature and pressure. Density measurements will be performed by means of a single sinker magnetic suspension densimeter, one of the most accurate techniques currently available. Speed of sound measurements will be performed with the highest accuracy by means of a spherical acoustic resonator. The ideal isobaric heat capacity shall be obtained from speed of sound measurements. Additionally, the National Physical Laboratory and the University of Valladolid will develop, test and compare new techniques able to produce reference hydrogen humid mixtures. These mixtures will be used as references for experimental techniques able to determine the dew point and water vapor enhancement factor in hydrogen-enriched natural gas mixtures. These techniques will allow to set a standard and calibration procedure for industrial hygrometers. The experimental data obtained in this work package will be compared to previous equation of state. They will be used to improve existing models and to develop new ones. The University of Valladolid, BAM, and Reganosa will participate in this task.